In my other videos on virtualization, I talked about some of the more general challenges, and what I'd like to do in this particular video is talk about some challenges that are specific to malware defense in virtualized environments, really thinking about anti-malware. Now, virtual machine instances, they run applications on top of a guest OS, which itself is running on top of a host OS, and as you can imagine, there is always a possibility that one of these applications is a malware instance. Imagine you've got some malware running on this particular virtual instance on top of this physical instance. And that malware instance might have gotten there because a security vulnerability was exploited, or maybe there was social engineering. But it really doesn't matter for the purposes of this discussion. Really, all that really matters is that we have to acknowledge the possibility that malware infestations on VM instances do represent a real risk, and I think that that's something we can all hopefully agree on. Now we do know that it's possible to get anti-malware software. Obviously, there's a lot of it available out there. So imagine, the naive way to handle this problem would be, let's say, to install a copy of some anti-malware software on each possible virtual instance. And as you can quickly begin to imagine, that this would not be a really good solution. And why is that? So um, the main thing obviously is performance. I think, and I'm going to just kind of write this out just because it's so critical. Performance, I think, is the most critical thing, or one of the most critical things when it comes to thinking about malware defense within a virtualized environment. Now, the reason for that is that, first of all, every endpoint now is a virtual instance, and so what you basically would have is when you have anti-malware software running on each virtual instance, that ends up, each of these things itself is using system resources. For example, every single or most of the major anti-malware technologies out there do have, let's say, a database of signatures that they store locally. Okay, so now you would have many copies of the signature database, one copy stored on each virtual instance that contains the underlying anti-malware software, and that's obviously very expensive, and that would just be a major waste of resources. That I think obviously itself might be a non-starter, and I think that especially considering you have to keep in mind that even though these are virtual instances, they're obviously all running on the same physical instance, and so there is a limit on how much on what system resources they have access to. Ultimately, they're kind of multiplexing a single set of system resources among them. Okay. Now, to make matters worse, I mean, we all generally know that many of the anti-malware technologies out there already consume a considerable amount of system resources at a baseline. And if you multiply that number times 8 or 16 virtual instances, that could start to cause, and in fact it would almost certainly cause, the underlying physical CPU to just overload. It might cause the whole instance to come crashing down, and that would not be a good thing. Now it turns out that there are some more elegant ways to handle the situation, and what I'll do is maybe give you one approach, and this will be, I'll try to describe it at a high enough level so that I suspect that most VM-aware anti-malware technologies out there will likely be implemented somewhere along these lines. So this is not meant to be a specific implementation, but something of a more generic framework or approach for dealing with this particular problem. So what you can basically do is imagine you can have one single VM instance, and it can be dedicated to security. And we're going to call this a security virtual machine, or SVM. So imagine you've got an SVM, and let's let this label be the SVM, okay? So the idea is that you have a single SVM, or security virtual machine, and this is the place where the actual anti-malware technology is running. So I'm going to kind of put this in gray. So imagine you've got maybe a small database, and you've got some actual software running for dealing with malware defense, okay? And what's going to happen is this SVM is going to really interact with these other machines. So in other words, you're going to kind of replace all these instances with a single SVM. And the SVM is what's really going to be used to interact with each individual virtual machine instance, at least when it comes to security. And how does that work? Well, at this point, what you really do need, and this is an important aspect of this type of approach, is you do need some support from the underlying hypervisor, since by design, virtual machines are designed, virtual instances really are designed so that, they're designed to be isolated from each other. And if you have virtual instances running on a single physical instance, they're not supposed to be able to know what's going on in the other instances. That's by design. Now, the good news is that some of the vendors who provide hypervisor technology do provide an API that gives some degree of visibility into different virtual instances. So what the API basically allows is now relevant, I guess maybe security relevant information on each virtual instance would be communicated to the hypervisor via the API. Okay, via maybe a particular aspect of the hypervisor, and then the idea is the SVM could then get access to that data and could then make decisions and help cause subsequent actions via the API, via the hypervisor to all the individual virtual machine instances. Okay, so the idea is that imagine you have let's say a new file that's being written to the file system. Let's say there's a file that's being written to this particular file system right here, and that file happens to be malicious. The idea is that because you have this setup in place, you'll now get data about that file that goes to the hypervisor via the special API, and then the hypervisor will then effectively, that data will get communicated up to the SVM again via the API, and the SVM now can look at this information that it gets about this file, and it can make a determination about the file by checking its local set of resources. It's only going to check the local set of resources rather than having something that's spread over multiple machines. And those local resources may also include, you could potentially go off network and maybe you could check the cloud as well, and use that as a way to make a determination about the file. Now the nice thing here is that, and I think it's the most critical point, is that the actual decision making is happening in one place, and all of the logic, the resources, the databases, etc., they really reside in a single place. They're not being replicated unnecessarily. And this type of approach can really, in my mind, it significantly tempers the system resources that are required to protect virtualized environments from malware. Now of course, other than trying to outright prevent malware, you also have to consider other dimensions of malware defense, such as improved visibility, improved control, and really things along the lines that we talked about in some of the previous videos. But the architecture I laid out for you, an architecture just kind of like this one that's represented in this video, can really be helped, really can be used to handle other dimensions as well. And so you can deal with issues like visibility and control, which normally do go down. So normally you do lose visibility in virtual environments, and you do lose control in virtual environments as well. We talked about that earlier. But a technology that kind of isolates a lot of the issues can also be used to help handle all different dimensions, not just performance, but visibility and control as well.